assignment of the semester. Coming out of these, be thinking if you know any graduate students or talking like next semester.
How long were you in terms of like
Okay, thanks, James. Well, it's my pleasure to introduce, actually, spelled Sanskriti dot, but it's pronounced Sunyaev-Zeldovich. Did I do that right? Okay. She was, she actually just learned that she did her bachelor's at Presidency University in Calcutta, and then a master's at IIT Bombay, Mumbai. And then I know her from OSU, Ohio State University, where she did her PhD with Sunyaev-Zeldovich. And now she's at Stanford, usually as a Kite fellow, right? And then now as a Hubble fellow, just started this year. Her talk is Where the Hot Universe Meets the Energetic Universe. And she's sort of a collaborator with me, so you haven't collaborated yet, but.
Thank you, Ben. Yeah, so it's nice being here. I think this is my second time in Colorado. I really had a good time first time, so I was like, okay, I should come again. I'm going to talk about the hot CGM today and where you can see the confluence of the hot universe with the energetic universe. But since CGM is not, I would say, a very common field, I should first introduce what CGM means and what CGM means in the context of today's talk. Roughly speaking, anything outside the disk of a galaxy and everything out to the virial radius is the CGM. Although virial radius is not an abrupt boundary and the CGM doesn't stop existing there, but that's roughly the definition of what CGM is. So by construction, it's a connector of the ISM, interstellar medium, to the IGM. And if you think of the gas flows inside the CGM and think of it chronologically, first the gas comes from the IGM, it gets shock heated and forms a fuzzy blob of gas. And when the disk forms, the outflows goes into the CGM. Part of it can recycle back to the disk, part of it can stay there forever, part of it can leave the galaxy forever, depending on its initial energies and all. So all of these inflows, outflows, and recycle happen in the CGM. So naturally, it controls the galaxy evolution a lot. But because of the very faint signal, CGM was kind of neglected for a long time. And you might see that ISM and IGM are significantly better understood than the CGM. But more recently, we have understood why we should study CGM and, of course, all the phases. And roughly speaking, CGM is multiphase just like ISM and IGM. Its density and temperature spans more than 2 orders of magnitude. So it's very richly multiphase. And despite being multiphase, we expect the most massive and volume-filling phase to be hot. Now, hot is very subjective. So in this case, hot essentially means the virial temperature, which also is a mass of the is a function of the mass. But in this talk, I'm going to focus on Milky Way-like or more massive galaxies. So the virial temperature is around 1,000,000 Kelvin or more. So in this case, hot primarily means 1,000,000 Kelvin or above. And what do we mean by the hot CGM? So the first component is the low density, very low metallicity gas that comes from the IGM and shock heated. A very small fraction of it cools and forms the disk, but most of it just remains there in the CGM. But the other component is denser, it's more metal enriched and often hotter. So there are two different components with very contrasting properties, and the details of their mixing decides what the physical and chemical properties of the CGM are going to be. So observationally, what we see is not just the first component, it's the integrated effect of the second component on the first one. And broadly speaking, why do we even study the hot CGM? And that is obviously connected to why we study the CGM in the first place. One is to solve the missing baryons problem. Now, cosmologically, we know the ratios of baryons to metals. In large structures like galaxy clusters, the ratio of baryons to metals are consistent with cosmology. But as you start moving from clusters to groups to galaxies, here you can see the interstellar medium and stars account for only 20% of the baryons. And that indicates rest of the 80% baryons could be in the CGM. Now, the cooler phases of the CGM has already been studied in UV in great detail. There is an abundance of data, but the problem is often the covering fraction of that cool phase is really small, so they might not contribute much to the baryons. And related to that problem is the missing metals problem. We know metals are formed inside stars. So if we understand stellar nucleosynthesis correctly, we know how much of metals we are expecting in a galaxy. And we can also calculate the amount of metals we observe. And here, as you can see, the metals in the interstellar gas and dust plus stars, that's again only 20% of the metals that is ever produced. So where does rest of the 80% metals go? Well, it might again be in the CGM. And again, in the cooler phases of the CGM, we find that there is obviously some metals, but there is a huge uncertainty in the ionization correction. And when I say huge, it could be from a factor of 10 to 50. So you can't really solve all the missing metals and baryons problem just by focusing on the cooler phases. You have to include the hot phase. And what is most important for the hot CGM is the missing feedback problem. Because if there are metals in the CGM, it has to be carried from the ISM to the CGM in the first place. And depending on the initial energies and momentum of that outflow, the fate of that outflow will be determined. It might come back, it might cool and be in the different phase of the CGM, or it might leave the galaxy forever. And the hot CGM is supposed to host most of the thermal energies. So when it comes to the missing feedback problem, hot CGM could be the answer. So I'm going to start with the Milky Way, which will be a significant part of the talk. And just like Sun is the best understood star, Milky Way will always be the best understood galaxy. No matter how well we, sample a large number of galaxies, external galaxies, because of our vantage point, we can see Milky Way from a different observing geometry that we can never do for external galaxies. And as I'll go along, I'll show you how we can kind of use existing data that are not used for CGM in a very economic way that we cannot do for external galaxies. So that way also, I would say Milky Way becomes kind of the poster child of galaxy to understand all the CGM in great detail. And then you can kind of project it to different galactic properties. And I'm going to talk both about X-ray emission and absorption. That way, Milky Way is at a very interesting temperature range. If the gas is too hot, like galaxy clusters, we observe it primarily in emission. If the gas is too cold, we observe primarily in absorption. But this is an interesting temperature where you can probe both emission and absorption. You can correct for all the biases that are present in emission or absorption and can get an empirically model-independent measurement. So traditionally, people started observing it in emission, and Rosat was the first time that enabled us to do this type of measurement for the CGM of the Milky Way. That time it was not called the CGM, it was called something like transabsorption emission, in the sense it's some emission that is passing through the absorption of the disk of the Milky Way, but eventually we understood it is the CGM. Now, if you have seen any X-ray image of bright objects like galaxy cluster, supernova remnant, any bright object, how do you detect that object? You need that image. You need to subtract some sky background to detect the actual signal. That sky background itself is composed of so many different components, and only one of them is Milky Way CGM. So it is impossible to do imaging analysis in this case because your image, your signal and all other components, they have similar radial profiles, so you can never subtract the images, and you have to do a forward modeling of all the spectral components together. And the main takeaway from this image should be these two bumps, as you can see. These bumps are from the two extreme ionization states of the oxygen, oxygen 7 and 8. And the main two observables are the temperature that comes from the emission intensities of oxygen 7 and 8. And there is an underlying continuum which gives you the emission measure, which is a measurement of density squared. So naturally, it will be biased to denser gas because it's density squared, but also because it is dominated by line emissions, it is biased to a temperature range where these metals emit the most, as in they have the highest emissivity. So you might have a large density and temperature space where the CGM is present, but emission will always probe a subset of that. Absorption, on the other hand, does not have that bias. So in this case, all the AGN sightlines has to pass through Milky Way CGM, and we can look for zero redshift absorptions. So there we can also see oxygen 7 and 8 absorptions. Same as the emission, we get the column density and the absorptions from the column density ratios. Now this is, yeah. Yeah. Yes, yeah.
So that's serious, but what you're seeing is nothing to do with what you'd like to see.
Oh, in this energy range, yes, this is aluminum and silicon lines. So it has,
Instrumental, that's
yes,
coming from the instrument.
XMM instrument, yes, that has no
Right.
effect.
What I'm trying to understand is why would one make such a terrible instrument? With the carbon, I think,
Rosette was the first one, but this is XMM. Yep. And in Rosette, you cannot do proper spectral analysis. Sorry, what? XMM? Oh, yes. But also, I mean, our emission is mostly at below 1 keV, so I don't really care what's happening here. I just need to include that in the spectral feed. I know, many people care. But Prism is better. Yeah. Prism doesn't have any instrument lines like that. So yeah, Prism would be better. But yeah, this is XML. Now, if we summarize the results in the first 2 decades or so, from Rosette, Chandra, XMM Newton to Suzaku, this is roughly the summary. Everything fit very well with each other. The measurement from absorption and emission, they were similar. They were roughly same across the sky. And since here you can see the dependence on emission and absorption are different, you can combine them together to break the degeneracy between path length and density. So it turned out that the path length is really large, primarily because of the absorption. And also the mass, assuming some absolute metallicity, is pretty large. So if you combine all the mass in the disk with the mass of the CGM, it's large enough to account for all the galactic baryon senses. So if you want to visualize how CGM looks like, it would be something like this: a very low density gas filling up 1,000 times larger volume than the disk itself. And that's what you expect. So everything is solved, right? The problem is there was 2 underlying assumptions in these calculations. One, all of the oxygen 7 and 8 are coming from the same phase. It's a good assumption to start with, but again, we can test. And the second is oxygen to all other metals, they have the solar-like chemical composition. It is again a good assumption to start with. I mean, if it is not solar, what would you start with? But again, in the data, we can test that. So for that, we take an approach of combining multiple metals and multiple ions of multiple metals and also multiple transitions. So in addition to oxygen, we look for hydrogen-like and helium-like, that is the 2 extreme ionization states of multiple light elements. And they span a large range of temperature range. Also, to account for any saturation in the lines, we combine multiple transitions as well. Now, while the principle sounds very easy, it is very tough to do it for X-ray spectroscopy because one, most of the transitions are very weak, so you need very deep data. And secondly, now the continuum fitting become extremely complicated because now you're not focusing on a small range with only oxygen. You are fitting a large range of wavelength. And that makes the continuum fitting very complicated. I'm happy to talk about that in more detail, but I'm now going to focus more on the results. So we started with one of the blazars with almost 1.8 megasecond of data. So that's a really deep observation. And we looked for the zero redshift absorptions that we expect to see, like oxygen 7 and 8 and nitrogen 6 and 7, neon 9. These are the lines we expect to see, and we also do see. But the strength of nitrogen and neon lines were quite large compared to what we expect. And also we see neon 10 for the first time in the CGM, which we do not expect in the million Kelvin gas. So something was happening. But again, this is just one sightline. So you need to follow up with more and more sightlines. And here we expand the metal set, going from carbon to silicon, just looking for more extreme sightlines. And here you can see we detect neon 10 again, we detect silicon 14, which is even more extreme. And in the other extreme, we see carbon 5. Now, even before any modeling, if you see carbon-5 in one end and silicon-14 in the other end, and you have so many intermediate lines in between, you immediately know you can't explain all of them with just one temperature phase. Yeah.
Slide with the ionization fractions so that we can kind of see where silicon 14 is, the solid line.
Yes.
And let's think about
It peaks at 7.2. Yes, carbon-5 is this. Yes, yes. Yeah. So this is kind of now imprinted in my brain when I look at this spectrum, because even before modeling, you know what to expect from the data. And we are now following up with more sight lines. We see neon 10. This one is not published, but we see magnesium 12 for the first time. So we are seeing a lot of extreme lines. But remember, these are very deep data, and it's not feasible to have such deep data, for a large number of sight lines. So we also stack the low signal to noise sight lines from the Chandra archive and give us 10 megasecond of effective exposure. So we look for these extreme lines again, and we detect silicon 14 again and sulfur 16 for the first time. So we have such extreme lines like neon 10, magnesium 12, silicon 14, and sulfur 16, which we do not normally expect to see in Milky Way CG. So now if we do hybrid ionization model to explain all these detections together, we find that the virial phase is obviously there, as you expect. And in addition to oxygen, we have many other lines that gives us a much better constraint on the temperature and other parameters. But also there has to be a supervirial phase that's distinct and almost an order of magnitude hotter and is probed by these extreme lines. But also what is seen normally in the UV and probed by oxygen 6 and neon 8, that can also be probed in the X-ray. And there are carbon, nitrogen, and oxygen lines that gives you a very good constraint on the temperature as well. But that is just about the existence of these different phases. In addition, when you have multiple metals, you can always calculate abundance ratios. And it looks like the abundance ratios are nowhere close to solar. And also it varies across phases. For example, if you take magnesium to oxygen, I'm not showing all the plots that you can see in the paper, but if you take any two metals and their abundance ratios, it could be solar in one phase, it could be subsolar in the other phase, it could be supersolar in the other phase, and so on. So not only the chemical composition deviates from solar, it varies across phases, indicating a lot of inhomogeneous mixing in different phases of the CGM. And up to this, I'm talking about just detections, but sometimes non-detections can be important as well. Now in the fitting, we don't just have light elements, we also have iron. And we started with assuming iron to alpha elements to be solar, but we do not detect any iron lines. So in the model, it predicts a lot of strong iron lines that you can see not present in the data. So we had to reduce the iron abundance in the model, effectively giving us an alpha enhanced CGM. Now this supervirial gas, this non-solar abundance of light elements, and this alpha enhancement, none of these were predicted in the theories of galaxy evolution, because for such an ordinary galaxy like Milky Way, you don't expect to see these things. And that tells us that we probably don't understand galactic outflows and feedback really well. Now, so far, we have been trying to explore the supervirial gas and the associated results in absorption. We want to see if we can detect it in emission as well. So we always choose a blank sky that's very close to a sight line in absorption, already with detection, so that we have a higher chance of detecting. And this is the first sight line where we found that indeed there is an hotter phase, which is probed by oxygen 8, and there is a cooler phase, which we already knew about, probed by oxygen 7. So same as absorption, oxygen 7 and oxygen 8 are not coming from the same phase, both in emission and both in absorption. So what was done in the first 20 years, assuming they're coming from the first, coming from the same phase, was okay in a 0th level assumption, but now we can see in the data that's not the case. So after XMM, we follow it up with Suzaku, then it has been independently followed up by the Helosat team and the Erosita team. The great thing is that all of the results are very much consistent with each other. We do need this extra supervirial phase in emission in 60% of the sky, unlike the virial phase, which is everywhere. And the differences are that the virial phase has a roughly constant temperature. The supervirial, on the other hand, that has a very variable temperature that we do not really understand. And consistently, the supervirial phase is fainter than the virial phase. Again, the reason we do not understand, but that's what we find from the data. And same as before, the emission measure varies across the whole sky. So do not think of the CGM as a sphere. It's more like an amoeba. It's very anisotropic. So that's the thing about the supervirial gas in emission and in absorption. But now if we try to combine everything, what do we have? Virial phase in emission and absorption, supervirial phase in emission and absorption. If we bring everything together, what do we see? One, the emitting phase is hotter in the virial phase than the absorbing phase. And one of the ways that can be explained is the emissivity bias of oxygen that we talked about before. So this is the whole range of temperature you can see in absorption, but this is the only temperature where oxygen 7 emission peaks. So even if the gas is present across this whole range, your emission measurement will always be biased toward a smaller temperature range. And that naturally explains that the virial phase in emission and absorption, they are indeed the same phase, and it's only the measurement biases that are giving us an apparent discrepancy. But that didn't work for the supervirial phase, because here the emitting phase is actually cooler than the absorbing phase. The emitting phase is consistently fainter than the virial phase, but the absorbing supervirial phase is consistently higher column density than the virial phase. So it's a lot of mess, and we try to understand what is causing that. Now, same as oxygen being the dominant component in the virial phase, first we try to understand what is causing this bias. So we develop a method called chemical tagging to find the relative contribution of different elements and find that iron is actually dominating this bias. So same as oxygen, if you look at the supervirial phase, the emissivity bias of iron will bias the temperature to a lower end instead of higher. So if you have an emitting and absorbing phase, both containing iron, because of the measurement bias, you will measure a lower temperature in emission than in absorption. But if you remember, we did not detect iron lines in absorption. Now, iron cannot be present and absent in the same time, in the same phase. That's logically not possible. So that tells us that the supervirial phase in emission and absorption, they are indeed two different phases. And their chemical enrichment tells us that they have different origins. We do not know what the origin is, but we are still trying to understand. And I'm not going to tell you that this is the final, relative distribution of the gas, but this is something that kind of is intuitively, comforting for us. So there is a inflated disk of supervirial gas in emission. Dense gas enriched in iron, so naturally came from some type of a supernova or all. There is a shell-like structure around that. That's the virial phase in emission, and that's the denser phase. Then the same phase has an extension that forms this spherical halo that we see in absorption for the virial phase. And for the absorbing supervirial phase, we don't know. So we have a lot of things to understand here, primarily in the context of galactic outflows. One is how was so much metal carried there, why it has not come back, why it has not been cooled, and what is keeping it hot, and so on. But now I'm going to slowly move on to the external galaxies. And I'm just going to take a small break and see if there is any remaining questions about the Milky Way. Yeah.
So the supervirial absorption phase, that has a column to 10 to the 20, but much higher. Everybody seeing in your
yes
class.
Yes.
And that also doesn't have iron in it. Yeah, so you think that's closer, like in your picture there?
No, this is the iron enriched emitting gas.
Okay. The supervirial, this supervirial gas, I think that's this
Supervirial gas in emission, that is iron enriched, that's closer to the disk.
Okay.
And supervirial gas in absorption that lacks iron, we don't know, because it is very random. So it is possible that, I mean, the problem is that we are also seeing it in stacking. So that's present all across the sky. Had it been just a few individual sightlines, we could escape by saying it's not present everywhere, but it is unfortunately present everywhere. So yeah, that. Now for Milky Way, you know, initially the first 2 decades were more on the detection of the gas, and now we are more into characterization. For external galaxies, detection itself is challenging because if you remember, the emission spectrum is already very messy with so many different components. And to separate that messy background, or the foreground in this case, from the signal is extremely challenging. And the challenge in absorption is that the absorption spectra is rich with information from redshift 0, which is good if you're trying to analyze Milky Way CGM. But that's a bad thing for external galaxies because you have very small redshift window where you have clean continuum and you can look for some redshifted absorption lines. So this is roughly the setup that you can expect for. Emission is a direct measurement. So as long as you can exclude the disk part, you can look for the emission from the CGM. For absorption lines, you always need a bright quasars that passes through the CGM, but it also has to be far enough from the ISM to make sure the ISM is not messing up your measurements. So unlike the Milky Way, where all AGNs has to pass through Milky Way CGM, this is not the case here. So I'm just going to talk about one example in emission, because this is the only galaxy with the detection. And the reason it's the only galaxy because we don't have data for other galaxies. But this is more of kind of a demonstration to show that even with existing instruments that were not designed to look for the CGM, we can still detect the integrated emission from the CGM, provided a lot of conditions are satisfied. So one is that you have to choose your target very carefully. You can't randomly choose, you know, a bunch of 50 galaxies and detect. And happy to talk about the target selection later if you are interested. And secondly, the standard method is that you take an image toward the signal, you take a background, you subtract, and you're done. That doesn't work here because we are noise dominated, and almost 90 to 95% of the photons come from the background. So the signal detection is extremely, extremely sensitive to how you model the background, which part of the sky you use for the background, and how you account for the variability in the background, both the spatial variability and the time variability. So we split the detection process into 3 steps. First, we look for the signal, that if something is there, then we try to characterize, is it some random fluctuation in the foreground or is it truly the CGM? And then we do the standard process of, you know, density and temperature profiling. So this is the integrated emission from the CGM, which is roughly, I think, 30 to 200 kiloparsec around the galaxy. So basically from here to here. And the region beyond that is used as our background. And as you can see, the main takeaway here should be the total data, which is the gray points, and the soft extra background, which is the dashed line that passes through here. And this tiny difference in the data compared to the soft extra background, that is the emission from the CGM coming from primarily the oxygen 78 and a little bit of iron 17. So that tells us how difficult extracting or separating the signal from the background is. And to be sure, we did this analysis separately with Suzaku and XMM, and we got roughly similar results given the differences in the instruments. And this demonstrates that even with existing instruments, it is possible to detect the integrated emission with decent-ish of the exposure time. And now we have been awarded roughly 450 kilosecond of time to constrain the density and temperature profiles. And yeah, that's the sum of everything else. Yes, call it background. Yeah. Yes, so the dashed line is everything except the signal. Yes. And if we want to compare it with you know, some of the simulations, so I think these are the data you sent me, Ben sent me at some point. So these are the predicted X-ray luminosity, integrated luminosity as a function of mass. And as you can see, none of the simulations are really consistent. Simba is obviously far off, but it is not, you know, exactly consistent for the other 2 simulations as well. And if we think of the luminosity as a function of other properties like star formation, there is a huge discrepancy among different simulations. So with existing instruments, we can actually make a smaller survey to just measure the integrated properties and see which simulation is, closer to the data, and then inform the next generation telescopes much better. But that's just about the emission. Now coming to the absorption, here we take the help of UV absorptions. So far I was talking about oxygen 7 and 8, but also there is oxygen 6, which probes a roughly 10 to the power 5.5 Kelvin gas, roughly cool CTM phase, or sometimes it's called warm, whatever you want to call it. Now, oxygen 6 probes a smaller temperature, which also means the thermal broadening is smaller because the temperature is going down. And at this temperature, you can also measure Lyman alpha. So if it is purely thermal broadening, you can compare the broadening of Lyman alpha lines and oxygen 6 and see if they follow the mass dependence. If it is non-thermal broadening, then again, there will not be any mass dependence. However, recently, some of the broad oxygen have been detected with unusually broad lines, but without any Lyman alpha detection. So had it been purely non-thermal broadening, we would detect Lyman alpha. Had it been purely thermal broadening, either way, we would detect the Lyman alpha line. So one of the reasons we see this broad oxygen 6 without Lyman alpha could be because they are actually coming from a relatively hotter phase that also contains oxygen 7. So for an extra astronomer, the job is really easy because you know the proper redshift from UV spectroscopy. You just want the quasar to be extra bright, and you know what wavelength to look for the redshifted oxygen 7. So far, we have been able to do this only for 2 quasar sightlines because most of the optically bright quasars are not extra bright. And also the oscillation strength of oxygen 7 is really low. But in both cases, we find the oxygen 7 absorption at exactly the same redshift of the oxygen 6. And in both cases, the nearest 3D galaxy is more than 100 kiloparsec away. I think in one case it's 110, in the other case it's 120. So it's well within the CGM regime, it's within the virial radius, but also it's far enough. So it tells us that the hot CGM can be far away from the disk of the galaxy. And also the column density is pretty large, implying that the mass of the hot CGM for external galaxies probed in X-ray absorption can also be quite large. So we get consistent result both from X-ray emission and absorption that with existing instruments, with some limitations, we can detect the signature. It can be extended far away from the disk, and in both cases in emission and absorption, it's quite massive. So the main motivation of these detections is that to demonstrate even the existing instruments are capable of detecting these signals, and we should make a better use of the existing instruments to inform the next generation instruments much better. So after this, I'm going to move toward the millimeter measurements. I'm going to take a small break just to get any residual questions for the extra part. Yeah.
Is there existing geometry?
Yeah, so we already know what the possible galaxy is. Yeah, yeah. In fact, that was already done by the UV people, so we didn't have to do that. Yeah. So yeah, in both cases, it's well within the virial radius, similar redshift, but also at a large impact parameter. Okay. So far we were talking about Milky Way and some external galaxies, but only individual galaxies and deep observations. Now I'm going to change from one galaxy to many, and by many I mean roughly 500,000. So there is a huge jump in the number of galaxies we are considering, but also we are changing the wavelength. We are now going to talk about the millimeter measurements, and I'll talk in a minute why we care about the millimeter measurements. So here we try to measure the thermal pressure in the CGM, in the hot CGM, using thermal Sunyaev-Zeldovich effect. It is essentially, you can think of a distortion in the CMB spectrum. So the actual CMB spectrum is a pure black body shown here in the dashed line. And as the photons from the CMB passes through any intervening ionized medium, the photons are inverse Compton scattered by the free electrons in the plasma, and the resultant spectrum becomes like this dashed line. So if you calculate the deviation in intensity as a function of frequency, you get this particular shape because of the thermal pressure of the electron. So this is the strongest kind of SZ effect. There are much weaker things which are not going to talk today. But this is measured by this Compton Y parameter, which is essentially a measure of the thermal energy or the thermal energy density. Now, traditionally, it has been used to study galaxy clusters because they have very strong thermal pressure, and individual galaxy clusters are detectable with thermal SZ. But in our case, since the signal is really, really small, you need to cross-correlate galaxy catalogs with the Compton Y maps to reduce the statistical uncertainty by almost, I think, 3 orders of magnitude. That's why you need million-ish galaxies to be able to separate the TSZ signal from the galaxy's CGM to rest of the background. Now, why do we care about millimeter while we can already do things in X-ray? One is that X-ray emission and absorption both have certain limitations. One, we are primarily probing metals, both in emission and absorption. We are not probing the total baryons. So you always have an underlying assumption of the metallicity. It could be physically motivated by other things, but it is never a direct measurement of the metallicity. But here we can probe all the baryons together. The other advantage, which in my opinion is the best advantage, is that SZ effect is redshift independent. While any spectroscopy dependent measurement falls as 1/r². So when you're moving to a larger redshift, it becomes really challenging to detect the signal. And that is the best advantage of the SZ. But also it has other disadvantages. One being that X-ray can probe the inner part of the CGM as good as the outer part because it has the angular resolution. In this case, the beam size is really large because these instruments are not built to study the CGM. So people don't really care if you can resolve the CGM or not. But when we can only get the volume average measurement of the CGM. So if you think of binned measurement, you will just have one bin in the whole CGM. So that is really complementary to X-ray because in X-ray, you are more inclined to the inner part. Here, you're getting the whole volume average measurement, and you can combine them to see if, for example, the simulations are consistent with the data. Now, same as X-ray, the CMB is also kind of, the millimeter sky is filled with many different components. So one needs to separate all these different components to get the measurement for TSZ itself. So think of a large region in the sky filled with say millions of pixels. In every pixel, you have to do this analysis to extract the Compton Y value. Kind of the same way we do X-ray, but the only difference here is that individual Compton Y value is way below the statistical noise. So once you cross-correlate, only then you can separate the signal from the noise. So what do you need for this? Well, obviously you need a Compton Y map, which I show in the right, and you also need a galaxy catalog. Now, the main work we focused on to see how you need to clean the Y map and clean the galaxy catalog to make sure that the interpretation of stacking is physically meaningful. Because you can randomly take a bunch of redshift and stack on the Compton Y map, but it would be really difficult to interpret that stacking data. So on the galaxy side, we make sure that we focus on the field galaxies, because if it's a cluster member, the cluster emission would dominate over the TSZ effect, and it would be impossible to separate the cluster emission from the CGM emission. Secondly, we explicitly remove all the AGNs, and we identify the AGNs in radio, infrared, and X-ray to make sure the AGNs are not biasing our measurement, because if it's an AGN wind, that will enhance your TSZ effect. If it's a cavity created by an AGN, that will suppress your AGN effect. And if you're stacking thousands of galaxies with some non-zero fraction of AGN biasing your measurement, it is impossible to track. So we just exclude them. And similarly, in the Compton Y side, we remove all the regions affected by clusters and AGNs, all the radio loud sources, at the cost of losing almost, I think, 40% of the data. But we have a very clean Compton Y map to start with so that we don't have that modeling uncertainty later on. So we cross-correlate and first check explicitly the effect of different contaminants. Here, all the red points are before correction, blue is after correction. So we correct for the cosmic infrared background and the residual effect from the dust in our Milky Way, and remove the galaxy clusters and the compact radio sources. So overall, the effect is that if you do not do these corrections, one, you underestimate the TSZ background. That means you naturally overestimate the signal. And two, once you model the pressure of the CGM, you might get a much flatter profile of the CGM because of these unaccounted for contaminants. So both in terms of the normalization and the slope, you might get an incorrect result for the thermal pressure if all of these corrections are not done. Okay, I'm going to share the result for just one mass bin because qualitatively they all look similar. So you take the galaxy catalog, you take the Compton-Y map, you cross-correlate and get a profile like this. And as I said, this whole bin corresponds to the volume average measurement of the whole CGM because we can resolve them. Now, this has three components. One is obviously your actual signal. One is called the two halo term because it's all the other galaxies in the background that are also getting stacked, and their CGM will have some non-zero effect. And the last component, which is often called the 0-point offset, which can be all other TSZ effects starting from the reionization to Milky Way's own CGM. Everything will have some non-zero effect. So we model all of them together, and we are able to separate the signal from the background, as you can see. And if it looks too technical, the main takeaway should be this black point, which is the data, the green hatch region, which is the TSZ background. The fact that the black point is above the green hatch region tells you that the TSZ effect from the CGM has been directly detected. Now, this is just one mass bin. You can repeat this for all the mass bins you want. So you get the thermal energy as a function of mass. Now, it has already been done for galaxy groups and clusters, where we already know that the groups start lacking thermal energy compared to what you expect. And if we extrapolate these measurements here, so if the CGM behaves like the groups, we expect a line like this, the gray line. Or if the CGM behaves like the clusters, that is, they're perfectly self-similar and the gravity is dominating the galaxy evolution, and not the feedback, you will expect this blue line. And the best fit line is the red one, which does not follow the blue line or the gray line. So clearly, the galaxies are not following the same evolution like clusters or groups. And initially, we started with just a power law because that's the simple one. But if you look carefully, the shape might actually be more like a broken power law, where the more massive ones are actually roughly consistent with self-similarity and have a flatter dependence on mass. But only when you start moving to lower and lower masses, the slope becomes larger. So a broken power law shown with this green line, that might be a better explanation than the red line. But again, with this data, we couldn't study it further because of the smaller sample size. And that's what we are working on now with an even larger sample of daisy galaxies, where things span across a large range of mass as well as redshift. So it allows us to split the quiescent and star-forming galaxies and empirically tell us whether this apparent shape of broken power law is because of different evolution of quiescent versus star-forming galaxies. So the analysis more or less remains same, and I'm not going to all the details of how we have improved the stacking analysis, but roughly speaking, this is how the radial profiles look like, kind of more or less same as before. As you can see, we can separate the one halo term from the background. And this is the thermal energy as a function of halo mass. And you can clearly see the quiescent galaxies do not have the same evolution trend as the star-forming galaxies. The quiescent galaxies down to a pretty low mass, like 12.6 or something, perfectly follow the self-similar relation. So they might have some effect of feedback, but that is not reflected in the thermal energy. So as far as thermal energy is concerned, they are perfectly consistent with self-similar and dominated by gravity. Only in the star-forming galaxies, we see a significant deviation from self-similarity, indicating that stellar feedback has a non-negligible effect on these galaxies. And if we try to compare them with simulations, we have just considered Eagle, TNG, and SIMBA, same as before. So all the data points are here, and you can see different curved lines for 3 different simulations. The star-forming galaxies in the data are more than an order of magnitude lower than all simulations. So for some reason, all the simulations are predicting very high thermal energy. That's not present in the data. But for quiescent galaxies, SIMBA is actually closest to our data. And if you remember maybe many slides, oops, what happened? If you remember many slides before, I was showing the results for NGC 30 to 21. Here, Simba was actually farthest from the data. But in X-ray emission, we probe the denser part of the CGM, which is closer to the galaxy. In SZ, we are probing the volume average of the whole CGM, including everything that's closer or farther away from the galaxy. So if one simulation is closer to the data for the volume average, but farthest from the data for the inner CGM, that implies the the pressure profile and the density profiles are very different in all these simulations that needs to be compared with the data. And what does that mean? That means just the integrated values are not going to tell us much. At a zeroth level, obviously, luminosity and thermal energy tells you which simulation is closer, but we need to constrain the density, temperature, and pressure profiles independently by resolving the halos to see at which radius, which simulation is closest to the data. And it is possible that different feedback mechanisms are dominating the galaxy evolution at different radius. So this is a work in progress, but I will leave you with this summary and take questions.
That was really nice. That was a whole array of Sunyaev-Zeldovich and X-ray emission network. We'll open it up to questions.
You had mentioned that the super big components were kind of patchy and not site.
By patchy, do you mean different emission measures or?
Right.
So both the virial and supervirial phase have different emission measures across the sky.
Okay.
So they are both anisotropic, but the virial phase has 100% covering function. So all the directions have the virial phase,
Okay.
but only 60% of the directions require the supervirial phase.
I see. Okay. So of those virial phases, still.
Yes. Yes. Yes.
So do you think the ST is needed to gain a comprehensive picture of CGM because of its ability to go to higher redshift?
O6 is different because that's in UV, so that you can go to even higher redshift because of the brightness, UV bright or optically bright quasars. But for X-ray, one limitation is, of course, the flux is going as 1/r². The other problem is that the oscillation strength, which gives you the actual strength of the absorbed tracer material. So oxygen 7 or 8 or all the other extreme lines I showed, all of their oscillation strength is really small. So the actual strength of the absorption line depends on the actual mass. Of course, more massive things will have larger strength, but also on the oscillation strength. And that's what makes it more difficult to detect things, even at lower redshift. And as you go to higher redshift, it's obviously worse. And yes, for SZ, the best, like the main strength is redshift independence. But remember, all the contaminants are also redshift independent. So that's kind of a pro and con of the SZ measurements, that your contaminants and the signal, everything is redshift independent. And anything randomly at any redshift in the background can also mess up your signal.
I have a question about the unexpected trend. Can you go back to a slide? Just like what's so unexpected about it?
So for the quiescent galaxies, I won't say it is unexpected because the zeroth level assumption is that it should be self-similar.
Okay.
If it deviates from self-similar, you can try to answer why, what type of feedback is making it deviate. But our advantage is that we are going out to 10 times virial radius, which is far enough beyond what the CGM can probe. So if the feedback is really strong and throwing the gas outside the virial radius, you should be able to detect that. And we do not detect that.
Okay.
So it's the non-detection that's telling us that feedback might not be strong enough to drive the evolution of these galaxies. So whatever the baryons are, they have to be inside the CGM. And in terms of thermal energy, that is the same reason it is following the self-similar relation down to a very like low mass. 12.5 is like almost like Milky Way. And for star-forming galaxies, this is unexpected because often, as you have seen in simulations, the thermal energy is an order of magnitude higher than what we see in the data. So there are two problems. One is the normalization. The thermal energy is larger in the simulation than the data. The other thing is the trained with mass. So this trained with mass. One thing is that what's the absolute value? One thing is that how it changes with mass.
Okay.
So in case of simulations, qualitatively, the simulations predict a higher thermal energy for all masses, but also it predicts a much flatter relation. Like if I just try to kind of, if you follow the cursor, suppose the simulation will predict the thermal energy of this mass bin here, but then it will be very flat like this.
Right.
While the data is showing a much steeper evolution.
So maybe there's not as much pressure in reality.
Yes. Yes.
Slots in your
Yes.
schedule, and if you want to meet with her, let me know right now. Thank you again.